Eric Robinson, who's a tech lead at Booz, and Rich Fetcher, who's a senior software engineer at RadiantBlue, will talk to you about how they're doing geospatial indexing atop Accumulo. So.
Hi. So I wanted to start out by saying how appropriate this is after that previous panel, because we started out at NGA, and now we open sourced a year ago, about roughly, under the Apache 2.0 license, and now we're working through the process of incubating within the Eclipse Foundation. There's a working group specifically for geospatial things called Location Tech, which seems like a very appropriate place for us. So we're working through that, and really where we see ourselves is kind of that conduit in between the scalable solutions of Accumulo and that sort of technology stack that it sits on. And then there's a rich geospatial ecosystem out there as well that we have tight integration with GeoServer, PDAL, which is the point data abstraction library, and MapNIC, and that's a map rendering engine. So through the various interoperability, we're trying to sort of bring the two worlds together. And we have a lot to cover, so we're probably going to move fairly quick. We're going to try to go over the core concepts behind it. And essentially at the core of it, it's a multidimensional index on Accumulo, and then we sort of special purpose that for geospatial and spatial temporal indexing. And then we'll go over some things you might find interesting on how, techniques we use in Accumulo to really scale out spatial data. So I'll let you cover.
That's a basic outline. What we're going to cover, I don't know how many people are familiar with GIS, so we're going to cover I'll just give a real overview of what the problem we're trying to solve. As Rich said, we did just a general purpose solution over multiple dimensional data, but our core focus was answering some critical problems with GIS. So we'll cover that. We'll give a very quick overview of what GeoWave is at a high level. And then we'll get on to the fundamentals, and then we'll cover some of the problems that we tried to solve, including deduplication and how we deal with some transaction isolation, map occlusion culling, raster data, and statistics. So general problem, we all see that GIS is ubiquitous now. It's everywhere, smartphones, GPS applications. So the idea behind it is, you have a general map, and then you're overlaying points of interest on that map. So points of interest, they're vectors. They're things like points, roads, boundaries. And at the general time, a question you might ask, you say, find me restaurants near me, or narrow down a specific space and show me what's in this area, broken out by different criteria. And then we have a ballooning set of analytics that we want to do on spatial data, including a density-based analysis and pattern discovery. So the features of GeoWave. So GeoWave is leveraging Accumulo, as we heard, and we do this because we've got the high performance ingest. We have horizontal scalability, and nice features. We get the per entry access constraints, and then the geospatial nature with the sorted row keys, we're able to get to fast geospatial retrieval. So right now we're integrated with, these are the tested versions. We do actually have a couple more versions that we support, but just to get a feel, these are what we've actually tested on a regular basis. So Accumulo 1.5 and 1.6, Cloudera, CDH4, CDH5, basically your Apache Hadoop 2.0. And we support for our services layers, which is our OGC for services, Open Geospatial Consortium services. We have plugins for our GeoServer using the GeoTools libraries. And we are slowly adding new features all the time. We have a whole set of analytics layers coming in. Our ingest framework is growing, and we have lots of RESTful data, different services for both ingesting, managing data, managing maps, and also to administer the application, do some monitoring. Rich alluded to some of the data types we're supporting. Right now, our core vector data types are basic simple features, and our grid formats are like ArcGrid and GeoTIFF. And we support a whole slew of different data types we're able to ingest into the platform. But the core data structures we work with on offering are simple features, which represent the vector data in the raster images. Like I said, we create this framework so it's very open. So any custom data type, it's very easy to add new types and new adapters for any multidimensional data. So let's get back now. Now you get an overview. Let's get back to the main problem we're trying to solve here. The main problem is we want to efficiently locate points, polygons in a bounding region. And we have this Accumulo structure, which is each table is organized in blocks sorted by row identifiers. So now we need some sort of two-way mapping between our multidimensional space and this single-dimensional row identifier. And the general problems that we're trying to solve here is we have, looking at this, expanding this a little bit, is so we have a multidimensional problem, translating that to a one-dimensional space. The second problem we're doing is we're dealing with different data types. So we have these scalars, and vector data scale is a point of interest. And then we also have intervals like time or polygons. And then the last problem we're trying to solve is we have a mix of unbounded and bounded dimensions. For example, we can consider space over a map as bounded by the bounds of the map, but unbounded might be considered time, for example. So how do we solve this? How do we map from multi-dimensional space into a single-dimensional space? Well, the solution we've used is space-filling curves. I don't know if you're familiar with space-filling curves, but basically, they're basically a linear traversal over n-dimensional space, right? So each point along your curve represents a point in your n-dimensional space. Now, as you can see from this slide here, there's a lot of different varieties of curves. So how do you choose the best one to do your mapping? And so there's a lot of papers, interesting papers on curve selection, and they use certain metrics. And what it really comes down to is this. So when I want to do a scan for a region, a multidimensional space, I'm going to create my bounds for that region. And that bound is going to represent a set of regions or a set of points over my curve, right? And those points may not be contiguous over that curve. They might be. So to get from my starting region to my stopping point in my bounds, I'm going to have to traverse the curve. And there's going to be stuff in that region that I don't want. That's extra, right? And so that we call that, there's different ways of measuring that. One's this thing called worst case dilation, which is really the distance along the entire curve versus the direct distance between my two endpoints of my bounds. And then another one's, a couple others, worst case bounding box, and another one's average bounding box. The worst case and average bounding box are basically looking at the area, the complete area of the bounding region versus just the area I need to look over my particular range. So I'm not going to go through all of these numbers. I just want to stand out. This is not. This is a paper we reference here that shows some of the shows these metrics. And I just want to call out that Hilbert does really well. And there's some other curves that do really well, but just if you haven't figured it out, we use Hilbert. And part of the motivation for that is because it does really well. Using these metrics, but the other reason is that there's code readily available. It's fairly well understood. We found a nice open source library that was developed by a person at Google, so that seemed like the natural fit. So now we're going to get down to attaching the curve to our particular problem, and we'll start with a two-dimensional case. The two-dimensional case is that we're laying basically a curve on a map. And so each elbow on that curve represents a cell over a map. And the granularity of those cells is determined by the granularity of the curve, or the precision. So in here, we have a 16 by 16 grid. And roughly that covers 22.5 degrees latitude and 11.25 degrees longitude per cell. And as you can see, one thing is about these curves, they're composable and they're nested, so they're kind of like fractals. So we can drill down to finer and finer granularity. And the way we achieve this is it's called recursive decomposition. And here's like a simple case where you can see it builds these natural quad trees. In this particular example, we're using what's a third order depiction with where we have basically 3 buckets per dimension. So, and we can see that from least precision to most precision from left to right on this little bit map. And so you have 2 bits, 1 for each dimension in this particular case. So taking that, going back, now we look at the curve, and we overlay our bounding region. And if you recall back, I said, well, we need to basically look at a scan, a bounding region from start to end, and we want to basically decompose and come up with a set of ranges. Now, you can see from this picture that this particular box covers 3 ranges of data within that box. And that's our scan over our row ID, linking back to Accumulo. One thing that's nice about these decomposition optimization is an optimization. So basically, a Hilbert's like a gray code. And what happens is there's a certain, what happens is that at the higher granularity, the entry and exit to a particular box is preserved. So even if through recursive decomposition. So I don't need to continue, once I determine that a complete box covers my entire scan range, I don't need to decompose any further. So in the middle, you can see the complete box. For example, there's 2 big middle boxes. I don't need to go beyond those bigger boxes. I can just note the start of the box and the end of that box, and I don't have to traverse and figure out all the points in between to determine my scan range. So let's go back and look at intervals in general. And we talked about the general case. Intervals are a particular problem where, for example, time intervals in a case of polygons. So a lot of times when we're talking about points, there's a point exists in a particular cell. Now we want a polygon interval which will cover multiple cells. In this particular case, I got a big yellow-orange colored polygon, and it covers 66 different cells. Now I want to query that cell, so I have a bounding region, and that's my blue. Now that intersects the polygon. So it's going to have, and those cells of intersection are going to be points along the Hilbert curve. Well, in order to be able to determine that polygon is in there, I need to through that scan range, I need to replicate that polygons in each of those associated cells. So in Accumulo sense, I need to have that replicated across multiple row IDs, that polygon. Once for each cell it intersects. So let's look at that a little bit closer. Well, that can be very expensive. You take a large polygon. In that particular case, it's only 66 duplicates. But you take something like the Pacific Ocean at 31 order resolution per dimension. That's 1.5 quintillion duplicates. So we need a solution for that. So our general solution for intervals is a tiered approach, where what we do is we use the capability of the nested granularity of the Hilbert curve, and we basically associate polygons at an appropriate tier to minimize the number of duplicates. So in this particular case, the blue polygon is at a higher tier, and it only covers it only has 3 duplicates at this higher tier. And you can see that the orange polygon's a little lower tier, and it covers only 4 duplicates. So the idea is, now with all these duplicates, you're going to have some false positives. So naturally, we want to minimize the number of duplicates so you don't have a lot of false positives. So in this particular case, this orange query region is going to return both polygons, those 2 polygons will be in the scan range for those cells that intersect with the query region. Now, so then we use the iterators on the tablet servers to do the final filtering. So the takeaway here is that the scan range for the boundary region, it translates directly to the row scan IDs, and then the iterators are used to filter the false positives. So how do we choose what the optimal tier to place a polygon? Well, it turns out that if you look, we look at a worst case scenario, in this case I'll just use a two-dimensional space, but the general case is for any d dimensions, there's going to be 2 to the d number of maximum duplicates. And the way we can see that is if you take the 2D case and you look at a cell that covers basically the center, an intersection point. And no matter how much you drill down, in all those tiers, it'll always have 4 duplicates, always. So that covers our intervals. So let's talk about the last problem. The last problem is unbounded dimensions. We chose to use something, a binning approach. So the idea of time bins is that a bin represents a periodicity or a particular interval of time or a period duration. And each bin is its own Hilbert space. So I have some examples here of time, 1997 through 1999. Each year in this particular time would be its own Hilbert space. And the bin ID is also part of the row ID for Accumulo. So up to this point, we've seen three components of the row ID. We've seen the Hilbert index ID, that's the cell ID. We've seen the tier, and we've seen the bin. Now, just a general case of the bin is basically we bin everything. Every dimension is bin. It just turns out that things like latitude and longitude aren't unbounded, so they basically effectively take their bin is essentially 0. And then any other bins, any other dimensions you throw at the bin, we do a combinatorics. So that, hopefully, I know it's quick, but that hopefully will cover the very basics of the general problems we're trying to solve. Now I'm going to hand it over to Rich, and we're going to look at more specific ways that some neat things we do with GeoWave and how Accumulo helps solve that problem.
So yeah, hopefully you understand why we want to preserve locality from n-dimensional space. So things close in n-dimensional space are also close in a single dimension. And we use that to represent our primary classes of geospatial data are vector and raster. For vector data, we have features and attributes. And so generally you have a geometry, and then you have various attributes also associated with that geometry. And we precede everything with that space-filling curve, locality preserving ID. And then what we have is an adapter, which represents the feature type, and then a feature ID. So each adapter gives a unique feature ID. So the combination of an adapter and a feature ID is globally unique in our system. And then, so we put those in the row ID so that we preserve whole rows, because as you can imagine, 2 features could have the exact same geometry, so the space-filling curve portion of it could be the exact same, so this is where we differentiate it. And then we have a hint to our deduplication, the number of duplicates, because oftentimes you'll just see one entry, so we don't want to perform deduplication if we don't have to. And then, so we have in our column qualifier, we have the attribute name. So we decided to generally keep attributes separate as column qualifiers so that we had attribute level visibility. So you can imagine one feature with multiple attributes. Some of them have different classifications, basically. And then we kind of inject that visibility through these field visibility handlers. So you just kind of tell us how, through this interface, how you want to handle the visibility on ingest. So with Accumulo, we can store a whole bunch of data, query it real quick, but at some point, there's going to be a problem rendering lots and lots of data. So you have a map request come in, and you're zoomed out over billions of entries. And we came up with a strategy. We have various strategies, and they're kind of optional, but if you really want your data to scale through map requests, this is how we found how to scale it. So one is, we call it Occlusion Calling, where we can figure out, based on your map request, what resolution on the space-filling curve you're looking at, and there's only so many pixels you may be able to render, so we're able to scale that way. So we can skip at that point on the space filling curve that represents a pixel. And actually, there's a better diagram coming up so essentially, if we were able to map your map request into various pixels at a certain resolution, once we know you've found a entry that matches that pixel, there's potentially, hundreds of thousands, billions. If you're zoomed out over the whole world, one city may have a billion points. We're able to skip all of that to the next sort of at the granularity of a pixel to the next area of the space filling curve using an Accumulo skipping iterator. So that's a very powerful technique that we're able to use. The problem is it really works well when you have this one-to-one mapping between your space filling curve and your geometry. And we lose that a bit with lines and polygons. Eric talked a bit about the duplication that happens, and the lines are blurred between exactly what the space filling curve representation is. So we also looked at distributed rendering. So within the iterator, we can sort of define this arbitrary transform on our data. And what if that transform was going from vector space to raster space, and we serialize a style over? We have the rendering code sitting within an iterator, and we render the style onto a map. You imagine each tablet server has different areas of the map, and on top of that, you might have different style rules, so overpasses versus smaller roads. So you have layering. And so we have these images coming back to GeoServer is kind of our general purpose rendering engine. So the map comes back from each tablet server, and then we composite it and then send the response to the user. So that allows us to scale a bit more. But without that idea of short circuiting large dense areas from a global request, we really aren't able to completely scale. So on top of that, we apply the concept of occlusion calling within the distributed rendering. So this diagram says a lot, and I'm just going to try to go quickly through the general concept. So if I'm doing my rendering on the iterator, I can define my for every pixel, I know where it is in the space filling curve and what range it represents on the space filling curve. And I can sort that list of ranges. And then as I'm rendering, I'm essentially masking out the areas that I've already rendered. So I'm eliminating things from that sorted list, and I know where I can skip to. So as I've rendered these polygons and lines, I know that I can skip, further ahead using the skipping iterator concept again. So that's one class of data. Then there's raster data, and that's similar, but it's inherently gridded. So we have basically the space filling curve represents a tile of data, and for the adapter we have the concept of coverage. So and you define a unique coverage for like a global raster data set that you want to store. Because tiles are unique, we can ignore duplication. We tile the data straight up. But if you are constantly collecting over the same area, we do allow the concept of merging tiles together. So with the image data that's stored in the value, we allow a sort of pluggable set of metadata. And by default, we store like no data values in there. I'll go over so for raster data and just global collection of data, you have spotty areas of collection. So no data is kind of important. Even for a single tile, the raster coverage doesn't necessarily snap to tile boundaries. So within a tile boundary, you have no data values. You have to be able to support that. And another important concept is we're not just storing like RGB images. We're storing multi-band sensor data that ultimately maps to an RGB image within our rendering engine. So here's kind of some of the advanced options we do with raster data, and all these things are kind of optional, and there's defaults for everything. But so there's that merge strategy, and it's anything you can define. So you define what kind of metadata you want to store with each tile, and then how you merge them together. So I listened to a Coverse talk about the aggregation framework, and we kind of use that same aggregation concept throughout our framework. So the idea is you might collect, like, over time, every 15 days you get new sensor data over this area. So you have a big pixel stack over time, and you want to apply some function to figure out what you actually want to show the user, present to the user. And we can do that within the iterator, so we store all the data, and perhaps your merge strategy is like most recent wins or highest score quality, highest quality wins. Because sometimes you get cloud cover depending on what the sensor is. Additionally, as we store data, you can give the option of keeping a histogram of all the data. So typically with the sensor collection, you might have a narrow band that's actually narrow amount of the band that's actually covered. So you'll get a very gray image if you were to just map that linearly to RGB. So with histogram equalization, we kind of spread that out, and you get that band stretching or better contrast in your image, which is typically just preferred high quality. And then we also have the option of storing an image pyramid with it. So the concept behind that is, the map request comes in. We don't want to do a whole lot of resampling in this interactive map. So we store a full image pyramid at different resolutions, so there's not as much interpolation and resampling going on within the rendering engine. So a little more on what we do with aggregation. There's certain statistics we want to store, certainly bounding boxes, counts. And we sort of, store that within Accumulo in a metadata table. And there's some interesting things we do as far as merging that together. So it's sort of back to that commutative monoid idea where, if, it doesn't matter, arbitrary order comes in, and I can just combine it together. And we store the different visibilities separately. So within our minor and major compaction, we have a combiner that will automatically merge things together. And then we also have a transformation iterator where we don't want to leak information about statistics from different visibilities. So our concept is that at scan time, the authorization of the user is handed to the scanner. And so if, let's say, the user has the authorization to see A, B, and C, stored separately would be A and B, and A and C perhaps, because we've seen those different unique permutations of visibility. But then at scan time, we collapse that together into a single statistic that the user will see. Another interesting thing we do with Accumulo, so Eric mentioned OGC, Open Geospatial Consortium. One of the standard interfaces that they support is called WFST, and that's WFS, Web Feature Service, and then T is transactional. So this idea that user can be writing to the index, to the data store. And with it, there's an idea of basically a user session or a sandbox where they're editing data that only they see, and they don't commit it right away. And then eventually they'll commit it, and it gets written to the global data set. So that's a bit of a hard problem to handle at scale, but we ended up using the visibility to handle that. So we sort of manage transaction identifiers with Zookeeper, and then as they're writing to their sandbox, we have a transaction ID that we associate with visibility appended, so that only they in their session can see. And then when they choose to commit it, then we end up removing that transaction ID, and it becomes part of the global data set. So I we've gone through the concepts. Now it's time for some eye candy. What can we actually do with this? Some good data sets we've played with is Microsoft Research GeoLife. It's just 3 years worth of GPS data. Various people doing activities with their GPS phone, and 17,621 trajectories, which doesn't sound like a lot, but I forget the total size of the data set, but the sampling of each trajectory is 1 to 5 seconds, so it scales fairly well. It's an interactive map where you can play with the points. That's sort of basic. Then you might apply an analytic sort of MapReduce job that we run that turns the point data into sort of a raster data, this kernel density heat map type thing. And usually that provides a user a little more value, a little more insight into what's going on. You can zoom around. This is interactive. It's a map. And so another data set we've played with is this GPX. So OpenStreetMap is kind of a crowdsourcing of street data, and they allow users to upload GPX to help people map street data. And so users uploading this GPX data ends up scaling to quite a bit, 2.9 billion points. So we ingested that, and using that map occlusion calling, we can render it at global scale interactively. You can zoom in. You can actually click a point. It's going to do an intersection with everything underneath that point, so you have to understand there's a lot of points potentially. You might want to zoom to a certain level before you decide to do that. But the idea is the attribute data is stored and can be retrieved through these standard web services. So again, kernel density applied to that OpenStreetMap data. A lot of activity around Germany. And then we can change the styling. So we're just storing the data as like sort of normalized density, and the color ramp that you apply to that is up to the user. So you can play with the styling and kind of have these cool effects. And that pretty much covers what we were hoping to cover. Any questions? Yep. So and through location tech, we're actually that's kind of a constant discussion, is there should be a general purpose library for space filling curves and what actually represents the space filling curve. And so we do have a space filling curve interface and a space filling curve factory, and we have a Z-order implementation. Z-order is fairly easy to implement. Research has kind of showed us that we default to Hilbert because it has that better locality properties, based on a decent amount of academic research. But yes, there's absolutely, and people have talked about a variety of, very unique space filling curve algorithms, and it's totally pluggable. So the question is there a way of sort of capacity planning or understanding how to index your data a priori? And we have talked through the concepts of kind of this vacuum analyze, given a sample of what your data looks like, how do you want to index it? It's a hard problem. So right now we have default configurations, and the configuration is sort of, programmatically configurable, but it would be nice to have just and one thing that sort of precedes that, and we've really gotten to the concrete proposal details within location tech of doing it, is geospatial benchmarking. So just the basics of being able to characterize performance, or how one curve impacts the other, and so that's sort of the predecessor to ultimately that vacuum analyze concept. Okay, so the question is specifically to ingesting GPX. Is it beholden to GeoTools, which is a library, a common library for geospatial things? And so the GPX parsing, the actual parsing of the format, is something that we wrote. And then there's standard objects within GeoTools that we sort of translate the GPX model into. It's called a simple feature in GeoTools. So at some point we translate into this GeoTools object model, and at that point, yeah, so it's sort of standard within at least the Java development geospatial community to use these GeoTools objects. So we reuse that. Does that answer the question? So as far as vetting on the format, what we handle, I mean, it's open source, so we'd love to accept contributions as far as, if it doesn't quite handle certain things within the format. I mean, sure. So this is one thing where, we talk back and forth with GeoMesa. So, I mean, both projects would like to just get on the same page, and don't want to diverge from each other and have the community not sure which one to accept. So we were in the process of open sourcing when we saw GeoMesa come out, I'll say that, and so we continued to open source. We would have just used what's out there and had the community have one. And we wouldn't have open sourced if we didn't think there were things that we did differently that we liked, and so we're not going to bash each other or anything like that. But it's certainly enough overlap that's a common question.
Yeah, I'll just add, from your speaking objectively, what's different? I mean, just to give you a couple examples, like the way that duplication's handled, for example. I think GeoWave has always been to focus on very general purpose. So we talked about general purpose solutions for handling intervals and handling multidimensional data. And so I think that's a differentiator from the API and how it does things. So I think, like anytime you have two different projects are doing similar things, there's going to be a lot of overlap, but there's also going to be different personalities to the product. And they're just natural differentiators. And I think it's just a matter of, they're both great offerings. They both do a lot of the same things. So this comes sometimes, and I think we're working together with them, as both localization of members, and trying to build more synergy, identify some of the key components that we could both leverage and move them into separate projects. So there's, I'm sure that relationship will grow over the next couple of years, and you'll see some exciting things come from that.
Yeah, there's a totally open line of communication. We're both in location tech and trying to work towards common goals. So on both ends, we definitely want it to sort of, converge at some point. It's just harder, easier said than done.